So, good afternoon to one and all present here. I warmly welcome you all for the last session of the Faculty Development Program on Sustainable Energy and Climate Solutions. Today, we are privileged to have with us Mr. Yogesh Kajale sir, Senior Vice President of the Engineering Planning and Design at PG Shirke Construction Technology Private Limited. He is a civil engineering graduate from COEP and brings with him over 35 years of experience in structural engineering, project planning, and prefab construction. Sir has been an instrumental in developing the precast and prefabricated construction technologies, designing high-rise structure and long-span structures, and contributing to the national standards and the committee under the BIS, CSIR, and CIDS. He has also published the several number of papers on the topic sustainable construction and earthquake engineering. Sir, we are very honored to have with us today. I welcome you, sir, and now I request you to proceed with your session. Thank you so much, sir.
Thank you. Good evening to all. Uh, Today, I'll be focusing on sustainable housing, particularly in multi-story construction and the multi-story construction used in mass housing. So basically, the India being a developing country, we have an enormous housing shortage, and that's exactly why the central government has announced PMAY housing schemes and boosting the housing in general. So today my presentation would be focusing on precast construction, how the precast construction is sustainable and how it can be implemented on a large housing scheme. I'll start the presentation. I represent, as briefly indicated, I represent an organization which is BG Shirke Construction Technology Private Limited. These are only two slides just to introduce what exactly is our contribution in precast construction and how we arrived at a sustainable solution to provide mass housing. The organization was set up prior to independence in 1944. And since 1944, initially we started construction using conventional cast in situ. And in 1970s, we introduced precast system for building construction. So during last more than 5 decades, we have achieved the requisite expertise, experience, as well as track record in delivering mass housing, in delivering the precast houses to the nation. So it's a more than 80-year organization. We pioneered precast construction technology way back in India, in way back in 1972. The factory was set up in 1970 and actual construction started using those precast element in 1972. The technology has been effectively transferred from lab to land. It's not that we implemented the technology without going into the requisite testing. With this technology, we had constructed more than 3 lakh houses in various uh, zones, in various seismic zones, in various weather conditions, and in buildings varying from ground story to 39 stories. Every year, we build almost about 200 lakh square feet. We have a dedicated workforce of 25,000 people working with us. The manufacturing units were set up in 1972, and the cost of plant, equipment, machineries owned by the organization is more than 1,400 crores. So that's the capital investment. What exactly is the system? Here, this is only a 5-6 minutes video, which will emphasize how the construction happens and what exactly is the precast system. I'll start the video. Is the voice of video audible?
No, sir.
Voice is not audible.
No.
So this was the video. Hello. हाँ, हाँ, नहीं अजून नाही आले रे. हम्म. आले की मी अपडेट दे. Yeah, sorry. The video, was the audio audible of the video?
No, sir, audio is not audible.
Okay. Anyway, there could be some issue with the audio. Uh, but the video was basically showing how exactly the precast construction happens. First, the components are manufactured in the factory. The factory is automated, fully automated. So there, the material consumption is the wastage is very minimal. Where the concrete is produced, it gets transferred to the manufacturing station with the help of buckets or shuttles, concrete shuttles. So the wastages in transporting the quantity or the concrete as well as the quantity of exact concrete is poured into the element. So that ensures that the material consumption is bare minimum, rather no wastage is happening. Now, how the sustainability aspect is covered in precast construction? Sustainability by definition is basically the practice of meeting present day needs without compromising the ability of future generations to meet their own needs. So, whatever raw material or the natural resources are available, we must be able to utilize them to the bare minimum possible ways. It involves holistic approach that integrates environmental, then economic and social dimensions to to create the society that can coexist with the planet on long term basis. This concept emphasizes responsible resource use, fostering social well-being and achieving equitable economic growth while protecting the environment for generations to come. Now, what exactly is the need of end user, particularly who occupies the houses? His requirements are bare minimum. He requires affordable initial cost. He requires reasonable amenities. He requires acceptable external appearance. He also desires to have the houses to be delivered in shortest possible time. That's speedy delivery. Then it must have secured enclosure, the community enclosure, then required usable area. The required usable area must be provided, and it should be maximum within the available built up area, and it should not required, or hardly any minimal maintenance should be required after occupying the house. Now these are basic needs of the end user, and who fulfills this need? The role is of promoter developer, could be a private developer or could be a government body, then architect who design the building, basically the architectural planning, then the structural engineer who ensures the stability and creates the structure which can withstand for the service life of that building, and the contractor, rather the constructor. So these are the four key element who ensures that the end users needs are catered with the sustainability and affordability. Now, as per Merriam-Webster, sustainable is basically defined as it's of relating to or being a method of harvesting or using a resource so that the resource is not depleted or permanently damaged. That means we should be able to recycle whatever is being used in the construction after expiry of the service life of that particular structure. It could be 50 years, could be 70 years, depending on the type of the structure. How a civil engineer can ensure the sustainability in housing? In my opinion, every civil engineer should ask basic three simple question: what, why, and when. What exactly is required? Naturally, obvious answer is strength and durability. Why? Because safety and sustainability. And when? Within the shortest possible time. Now these three questions has three answer but one solution, in my opinion, and that solution is precast construction. Why? Because it ensures judicious use of construction material, reduction of wastage of materials, reducing emissions during the production of construction materials as well as product, using more durable materials because the water cement ratio is bare minimum. The casting is happening in the factory under a covered shed. Use of products that contribute to safe, healthy, and built environment, use of materials which can be recycled, and use of construction system which minimizes pollution, particularly air, water, as well as noise during construction. So these are the prerequisites to meet the sustainability in housing construction. With this background, if we look at what exactly is the heritage of our of India, see, precast that way is not a very new construction technique which is being discussed or is being adopted in today's scenario. If we look at the Taj Mahal or the temples or forts, we will see that all these structures were precast. What exactly was the precast? It's not made in concrete, but it made in stone. Precast is basically manufacture the element away from the construction site and then transport those elements to the construction site and then assemble and joint effectively so that the structure can be erected within the minimal possible time, and the structure can sustain all the intended loading conditions as well as climatic conditions and disaster in case it happens so. like storm or wind or earthquake. So these monumental structures are basically our heritage structure, which are precast, not in concrete but in stone. Not because concrete is not sustainable, but due to it that it was not invented at that time. Had the concrete been invented during those days, our ancient must have also used the same concrete to produce these kind of structures. So precast technique is that way not new, nothing different for us. Now, when we talk about precast, the first question, the sustainability is basically that the structure, whatever is created, must give full service life during the life of that structure. How will it be ensured? Unless and until we 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 assess the performance of this system, no one can guarantee that precast construction system will sustain the intended loads. And with this basic prerequisite, it is essential that any new innovative system must be tested on full scale. What exactly is full scale? Full scale doesn't mean that if we are going to build 20-story building, then entire 20-story building is to be tested. Full scale is basically that it should accommodate all the types of joints which typically goes into building construction, and a minimum 3 level structure is to be subjected for simulated earthquake loading. That exactly is what full scale testing. We have various Indian standards. However, these standards do not provide the full scale testing requirement of a building structure. Adopting new technologies without adequate theoretical and experimental validation can certainly result into disaster similar to that happened with school buildings during 2001 Bhuj earthquake. You might be aware in Gujarat there were 6,000 precast schools which were built in 1997 to 2000, and then in 2001 Bhuj earthquake happened. During that earthquake, 73% of these school buildings, those buildings were single story, 73% of school buildings were collapsed and damaged severely. So untested technology, if implemented, it will not result into sustainable construction. Modeling, analysis, and design, as well as construction of RCC precast structure is very complex phenomena, particularly in absence of formal standards and guidelines for them. We do not have detailed guidelines and detailed standards currently for precast construction. Casting, erection, and jointing are important challenges which demand expertise in execution, and all these are coupled with skill supervision. In many of institute or even in colleges, the precast construction is not being dealt thoroughly, and our engineers are truly unaware of precast construction, the intricacies of that construction, intricacies in design of this particular system. We have one Indian standard which talks about ductility, and ductility is very important, particularly in case of seismic design. IS 13920 is that standard that recommends precast construction can only be used if they are designed to provide similar level of ductility as that of monolithic RC structure during as well as after an earthquake. So 13920 Indian standard doesn't ban precast construction, but in fact it promotes. And while promoting the precast construction, the standard recommends that it must be ensured that the precast system must provide similar level of ductility. In a simple word, what exactly is ductility? Ductility is an ability to undergo deformation without collapse. Lauchikta. So ductility is basically that. With this background, Central Public Works Department, which is an apex civil engineering body in India, they have come up with two office memorandum which highlights on the requirements of full scale testing. So that office memorandum provides how the representative sampling is to be done for full scale testing, what should be the loading protocol, and what should be the acceptance criteria. So, in India, we have detailed guidelines on full scale testing of precast construction. Our experience in India is that these school buildings I just mentioned in 2001 during Bhuj earthquake, these buildings were precast, and all these 75%, almost 75% buildings were damaged and collapsed. There is one test which has also been conducted at one of the leading laboratory, particularly at CBRI Roorkee, on 3D volumetric prefab structure, and this structure also doesn't perform to the acceptance criteria. So the criticalities of jointing, the criticalities of structural configuration, the selection of jointing is very crucial in precast construction to make the building sustainable. We have these two glaring examples how the precast structures have failed in India. With this background, we also decided that we must provide the solution to our nation, which will be perfectly suited to our seismic conditions. And with this background, the full scale testing program was undertaken by our organization, not recently, but long back. In 1984, we started the testing, whatever test facilities were available during those time. Now, why full scale testing is essential? The claim about safety, stability, and resilience of any building construction technology has merits only when the same is subjected to intended loading on full scale rather than simply relying on assertions. With the growing demands of construction of tall structure, it is extremely important to ensure that every component with its connection that goes into the building structure is tested thoroughly to ensure that the system performs to the desired specification. The inherent difficulty in replacing damaged or underperforming product once it is installed in high-rise building is quite obvious as it involves a lot of expenditure. Sometimes it is virtually impossible to carry out any repairs due to non-availability of access, and the resident of the buildings will have to live with the problem for the rest of their lifetime in that building. So full-scale testing ensures correctness of four parameters. One is design, the second is detailing, the third is production, and the fourth is installation. So after thorough testing, all these parameters are established and assured. It's as simple as that. Whenever any student gets admission into college, and if the student attends the college regularly, he is not declared pass unless and until he faces the examination, and then the he faces the test, and then only the student is declared as pass. So merely relying on the presumptions or assumptions of design, no construction system can be considered as a system which will perform on the design assumptions or design parameters. That's the reason why full scale testing is very essential. The left side is the photograph of the production unit, how the production happens. On the right side and the middle one is the precast buildings, which were constructed using the system which I have described earlier, that is 3S system. When we started 1970s, we have conducted various tests on 3S prefab within with the facilities whatever were available during those years. It started in 1970s, and in 2025 full scale testing were also completed. These are the few photographs how the testing happened on a sub-assemblage level, on a component level, as well as on a full scale level over the period of last 5 decades. Recently, I'm going to share with you how the full-scale testing has happened on precast construction to ensure that the system is sustainable. The first test was conducted on a representative model or rather on a representative full scale building, which was of steel plus 24 story. The critical floors were extracted from that particular building, and those two level structure on the left side, those two level structure was subjected to reverse cyclic push pull loading through actuator. Then the middle one is again a column beam slab system. The bottom story is a soft story, no wall pan, no walling. The top story is again a soft story, and middle story was considered as an investigation story. Again, this represents the real size building of steel plus 22 story. On the right hand side, this is a precast RCC load bearing wall panels and the slab. This real size building is steel plus podium plus 30, that is 32-story building. And this particular structure is a four-room structure of that 32-story building. These three structures were subjected to pseudostatic reverse cyclic loading. The left one was at Roorkee, and the middle one as well as right one was at MNIT Jaipur. After testing, the hysteresis were plotted, and what exactly is the ductility that was ascertained, and it matched with the provisions of IS 1893. The cracking pattern was also studied, how the cracking happens, and then the backbone curve was analyzed. This was the first test which was conducted in 2010. Then the second test, there were on the column beam slab structure, two tests were conducted in both the orthogonal direction, and on wall panel structure, three tests were conducted. These were conducted at MNIT Jaipur. This is a short video of the first test. See, in this is a time scale video. You can see how the building is getting deflected. Total 20 hours this test was going on, and we deflected this building to the tune of 120 millimeter. So the first test, rather first two tests on that column beam structure, total 20 hour the loading was going on. The loading was basically a cyclic loading with the actuator installed at top of that structure. Cyclic loading is basically, it's a displacement control loading. So from 0 to 1 millimeter, 1 millimeter to 0, 0 to -1, -1 to 0. Such three cycle comprises of one cycle. So from whatever is the resistance to displace that structure to that particular cyclic loading is recorded, and that is considered as the capacity for that particular cycle. Each cycle was then repeated three times, and then 1 millimeter, then 2 millimeter, then 3 millimeter, like that. And after 10 millimeter, a 5 millimeter increase in the cyclic loading was done. Up to 120 millimeter, the structure was displaced. The capacity of actuator was 100 metric ton. It's a servodynamic actuator. 100 metric ton was the capacity, and the capacity got exhausted. No major cracking happened for that first structure, and then the test was stopped. The drift recorded was well within that 0.4% of the permitted drift, and the resistance was 5.68 times the design base shear. So the test has passed. The ductility was also ensured. After completing those two tests, we also conducted the test on wall panel, precast wall panel and slab. This video shows the same test. Here you will find that the displacement is hardly anything, because of the reinforced cement concrete walls, the stiffness of structure is tremendous, and it resisted lot of load in a lesser displacement. For this structure, there were two actuators installed at top, each of 100 metric ton capacity. So the structure was loaded by for 200 metric ton load. After completing that, we cut the building, the same building. This building was of a 4-room building. The building was cut vertically so that the stiffness is reduced to half. And then again, the building was subjected, after first earthquake shock, the building was subjected to another earthquake shock, earthquake event. On the left side, you will see how the building is getting deflected. Here you will find that the displacement as compared to the first video is bit larger because the stiffness is reduced and the capacity of actuator is same, 200 ton actuator. Here you will find that no major cracking, rather hardly any cracking has happened. So the building is actually physically deflected. This is a reinforced cement concrete building. So after completing that loading on that part, then the singular part, which is a leftover part, that was also subjected. On the right side, you will find that. I'll play that video. The standalone part, this particular part, was subjected to load with this actuator. And here, since it's not a symmetrical part, you will observe that the building is actually getting subjected to torsion. This particular part is subjected to torsion. No joint opening had happened. No severe cracking has happened. So this was the fifth earthquake event on the same structure. So after loading this and after observing how exactly was the crack pattern, the major revelation is that this particular building could sustain 5.65 times to 7.81 times design lateral load, and the drift was in the range of 0.33% to 0.97%. In seismic design, it is very important to know how the structure will fail. The structure should not fail suddenly, but it must deflect so that there is an adequate time to evacuate the people or the occupant, and structure should be in a repairable manner after completing that earthquake event. So the building, we tried to increase the drift to understand how the building is going to collapse or how the joints will collapse. But we found that even after increasing the drift to the tune of 0.97%, the permitted drift is 0.4%. Still, no joint was opened and the building could sustain the loading. So our major takeaway from these experimental investigation is that the role of independent performance testing lab has gained importance in last few years to do the simulation of worst loading condition as per the design criteria. and putting the truly representative full scale specimen of real size building through a series of tried and trusted procedures to validate the theoretical assumptions used during design. Once a representative full scale specimen is tested to the specific and specified conditions and certified, the design, detailing, quality of production, and installation methods can be safely assumed to deliver the value it is expected to provide. So that's the major takeaway of, of this experimental investigation. I must say that this our prefab system, that is 3S prefab system, is the first precast technology to have been tested in India on full-scale real-size building specimen to prove its acceptance as laid down in Indian standard as well as CPWD guidelines. A similar testing protocol shall be employed for other system technologies which do not have formal standard for their analysis, design, and detailing. It is very important to use only those technologies through the experienced technology implementers which have been tested on real size full scale specimens and proved its credibility in terms of strength, ductility, as well as resilience. After doing this, then only one can say that my construction is a sustainable construction. This is very particularly essential for those technologies or system that do not have formal national standards, and hence all the stakeholders should promote only such technologies which have been tested and demonstrated to perform well under intended loading conditions in India. Apart from those tests, how the sustainability is ensured? See, the sustainability is basically whatever natural resources we are we are consuming in construction, those the use must be optimal, and we should not require to carry out repairs and maintenance every now and then. So the critical factors are basically stability. That stability can be addressed through performance testing, full scale testing, the structural stability. Apart from that, there is another important parameter, that is a after constructing the building, there must be some additional test which will ensure that the construction is also happening as per the acceptance standards and uh, provisions. So floor load tests are also required to be conducted, and we do conduct such tests on representative floors selected at randomly. The provisions are there in IS 456 how to conduct the floor load test and what is the acceptance criteria. So floor load tests are conducted. The loading is given with the help of concrete blocks or any other sandbags. Apart from floor load tests, the wet areas, particularly the balconies, then the bathroom, toilets, those are subjected to pond test, a water pond test, and whether any seepages or leakages are happening, that is also ensured. Now, I'll just show you what exactly, where exactly this system has been used. These are basically the case studies. This project is mass housing project at Taloja, wherein we built in three phases. The first phase was of 15,000 houses in a buildings of G plus 14 story. The second phase was about 8,500 houses, again G plus 14, and few buildings were G plus 22 stories. And the third phase comprises of 24,000 houses in a buildings of S steel plus 26, 27 stories. So these are the actual photographs of the construction site. You will find that there is hardly any prop or shuttering material required at site. The construction sites are relatively neater and cleaner as compared with the conventional construction. So this construction technique or precast construction technique is more sustainable and more adaptable to these sustainability aspects. Even the retaining walls, the water tanks are also constructed using precast wall panels. So a minimal shuttering material is required. The embodied energy that goes into construction is thus restricted to bare minimum possible. Again, the minimum number of labors are required. So the resources which are required for construction are to the bare minimum possible in precast system. And what is the outcome of this? See, the first project, the case study reveals that the delivery, the completion of flat is 9 flats per day. When the project started and when the project was finished, that duration, and in that duration, how many flats were constructed? We constructed 14,839 flats in 1625 days, working days. So the delivery is 9 flats per day. This delivery, no other system can give 9 flats a day. The conventional system is absolutely in conventional system, it's absolutely not possible. So this system, the precast construction system, ensures faster delivery in a minimal cost and with a minimal resources. The second phase, which was completed, there were 305 buildings, total 5,441 floors, and houses were 37,996, almost 38,000 houses. These, these homes, the houses were constructed in 2016, 614 days. So the delivery is 15 flats per day. What exactly this project has ensured? The speed, the strength, the safety, as well as sustainability. All four parameters can be established or rather can be achieved if we deploy such systems which are tried, tested, and proven on each of their credentials. So in the first case study, you find that there were 9 flats per day was the delivery. In second case study, it was 15 flats per day. These are few snapshots of ongoing projects where even the basement is also being built using precast wall panels. So on the left side, left down photo, this is a basement construction happening. On right side, the basement retaining walls, and then on the top left side, the podium level construction with precast columns and beams. These are the snapshots of that project. This project is under construction at Tathavde, Pune. This is a commercial building where the column grids are 8.5 meter by 8 meter. It's a commercial building. Heavy loading is there. So the column sizes are little bit larger. So lot of works have been constructed with precast construction system in various parts of India. Apart from us, there are many other players who are also using precast systems. And after completion, these are the few photographs of few selected projects, how the building looks like. You will find that once the building is completed, no one can distinguish whether it is with precast or with cast in situ or with any other construction system. So the adaptability to the end user is, there is no question of adaptability. The left side project is at Bangalore. There were 648 dwelling units only, 1.73 lakh square meter was the built up area. The right side is again at Morwadi, Pune, 863 dwelling units. So the aesthetic, any architectural features can be integrated in the precast engineering, precast planning, and the components can be manufactured accordingly. So there are basically practically no limitations per se. The project cost could be 133 crore or could be even 2,400 crore. These buildings are Sidco project where the project cost was 1,125 crore. See, in the earlier slide, I explained it was the cost was 123 crore. The another project is 1,100 crore. This project is at Delhi. Delhi is in seismic zone 4. There we built 11,400 houses in the first phase. The cost was 4,800 crore. Any elevation or any aesthetic is possible in precast. This is another project at Taloja, Navi Mumbai. This is of EWS and LIG houses. The cost of project was 3,374 crores and dwelling units were 14,800. The buildings were steel plus 25 and 26 story. This is the the highest high-rise building which has been constructed in India using precast. This is one of the top 6 building all over the world in precast reinforced cement concrete construction. This building is at Pahadi Goregaon. The height of this building is 119 meter, almost 120 meter, and the building is of 35 plus 3 podium and 1 steel. So total 39 story. This 39-story building was also completed using precast component, and prior to construction of this building, the full-scale test was conducted. So this is what is the sustainable precast construction and how the sustainability aspect as well as quality aspect have been incorporated and integrated into the precast building system. The last slide shows the 80-meter high building, 100-meter high as well as 120-meter high. So far the highest building which has been constructed using precast reinforced cement concrete in India is 39-story building at Goregaon, Mumbai. Was constructed by us only, designed by me only. It's a 120-meter high building. With this, I end my presentation. If you have any questions, please feel free.
Sir, were any design consideration for joints and connections are done to ensure the seismic safety of the structure?
Sure. Shall I show you how the detailing happens?
Yes, sir.
Yes, please. Let me open that. Yeah. See, initially the planning is done that where to locate the shear walls or columns, how many components are to be identified, how many components are required for that particular construction depending on the cranage capacity. So the first exercise is basically planning of the members. And I'll come to your specific question. Okay.
Okay, sir.
See, the members in seismic resistant design, it is very important that the precast system, whatever will be used, must be an emulative jointing system. What is emulative jointing system? Emulative is basically which emulates with cast in situ construction. The critical parameter is that to get the integrity and ductility and robustness, it is very essential that the reinforcement of one element gets anchored into the adjoining elements through in situ jointing. The system shouldn't have a dry jointing method. So, for high rise construction, we have come up with a peculiar wall, shear walls. The walls are basically on the left side, the bottom photo shows that the walls, when they are manufactured, when they are precast, they have a hollow inside, and these walls get erected at site, and then in the hollow part the reinforcement is placed and this portion gets concreted. So also the beams are partial precast, the reinforcement from the beam ends gets anchored inside the column or these cores. The staircases are also, the reinforcement is projecting above, that gets anchored inside the beam or adjoining slab. And the slabs are also half slabs. I'll come to the joint detail. Okay.
Yes, sir.
See, this shows that the lower story walls, the reinforcement is projecting above from the core, and this precast wall is erected. These There are hollow cores. This reinforcement gets anchored inside the core, and after erection, the core gets concreted. One second, I'll come to that. Now, this is the jointing method. On the left side, this is called as emulative jointing system. This middle bottom photo shows a dry jointing system. The dry jointing system is not recommended in seismic prone areas. On the right side, you will see that the precast element has a reinforcement protruding out from the edges as well as from the bottom. And then this joint is concreted after erection at site.
Okay.
So this is the drawing, the schematic drawing, how the elements gets connected. The bottom part is a plan wherein the shear wall is shown, and the darker side is basically a beam. The reinforcement is projecting out that gets anchored inside the core. On the left side also there is a beam. The reinforcement gets anchored inside the core. If we take a section, vertical section, this is how is the reinforcement arrangement at the beam wall or beam column joint.
Okay, sir.
Then at the foundation level, the reinforcement gets projected above. This is a pile. Basically, for this building, there was a pile foundation. So after completing the pile, the raft is cast. The pile raft is cast. From the pile raft, the dowels are kept. On these dowels, the upper wall gets erected. The stem wall gets erected. And then the hollow portion gets concreted after erection. This is another joint detail. This is a beam, then the column or vertical element, then the slab element, and this is how the reinforcement gets anchored from one element to other element. In the emulative jointing system, it's not 100% precast, it's a partial precast. Almost 80% concrete, or the elements of 80% concreting is done in the factory, and the 20% concrete happens at site after erection. This 20% cast in situ concrete facilitates anchorage of reinforcement from one element into the other element. Is that clear now?
Yes, sir. Yes, sir. Sir, one more question I had. Can we use sandwich panels or ferrocement or any other such type of thing if for precast construction?
Yeah, we can use the sandwich panel. There is only one rather, the sandwich panels can be used as non-structural panels, because sandwich panel necessarily has, one is a concrete panel, another concrete panel, and in between two there is an insulation layer.
Yes, sir.
So these two concrete leaves do not have interconnections, and
Yes.
if two leaves do not have interconnections, that performs very poorly, particularly in case of lateral shaking. May it be under wind, may it be under seismic. So such panels can be used as a non-structural panels, non-load bearing elements.
Okay. Okay. Okay, sir. Thank you, sir.
Thank you.
Thank you, sir. Any other participants have any question?
I think there are no questions.
Yes, sir.
Sir,
In online, actually, very few people ask the question.
Yeah,
Yes,
that's the reason why. That's the reason I
I have
always
one
prefer.
question. Hello,
Sorry.
sir.
Yes.
I have one question. Sir, as nowadays terrorist attack has been increased in number, sir, if the same building is exposed to the blast event, how can we ensure its sustainability?
Sorry. I couldn't get you.
Sir, nowadays terrorist attack has been increased in number. If
Hmm.
the same building is exposed to the blast event, how can we ensure its sustainability?
The building can be designed even for blasting actions.
Okay.
See, see, the criticalities are only in case of jointing. Now, when the system has the ductility, basically what exactly is needed in case of blast action, the design under the blast action, the structure must have adequate ductility. It's not that the structure should be completely resistant for the blasting action, but structure should be in a manner which can be repaired after a certain level of blast action. That exactly is the basic design principle even for seismic design. See, for seismic design, you all know that, say for example, if it's a seismic zone 4, then the maximum earthquake, MCE, maximum credible earthquake, is 0.24. For what forces we design the structure? Z by 2. So we reduce the credible earthquake to design level earthquake and by 50%. Then again, this 50% is reduced by response reduction factor. Now, what exactly is the response reduction factor? The response reduction factor is basically how the structure will respond to the earthquake event or to a blast event. In case of column beam frame structure, the response reduction factor specified stipulated by Indian IS 1893 is 5. So we reduce that DBE again by one fifth. That is, first we reduce by 50% and then we reduce it to 20%. That means we design only for 10 to 12% of maximum credible earthquake. Then what happens? Why this 10 to 15% design is considered to be safe and acceptable? It's only because the structure has that level of ductility. So structure will undergo some cracking, but it will not collapse and it will not endanger the lives of the occupant. There will be adequate time, enough time to evacuate the occupants, or even if the occupants are not evacuated, nothing will fall on the occupant and there won't be any life threatening in that structure. So that's the design principle. The same principle can be adopted even for blast resistant design. Apart
sir,
from that, there are another provisions which are also incorporated in this design. Those are progressive collapse provision. In case one element collapses, the whole structure should not collapse. That is basically a progressive collapse mechanism. That also gets addressed in the construction. May it be precast, may it be cast in situ. I hope I have clarified your question.
so sir, can we say that if we have designed a precast structure for seismic resistance, so can we say that it will perform okay, like desirable in blast as well? Can we
See,
ensure that?
if the blast, there is an Indian standard on blast uh, plus loading also. If the seismic zone, let's say Mumbai lies in seismic zone 3, Nagpur lies in seismic zone 2, Delhi lies in seismic zone 4, of course, those zones will get upgraded in the recently revised Indian standard. If the blast is equivalent to that, then yes, if the structure is designed for seismic activity, it can resist the blast to that extent. But if the blast forces are more than the seismic design force, naturally the governing case will be the blast loading, not the seismic loading.
Okay, sir. So, is any research going on related to blast or any other related to seismic also? Any R&D project?
Sorry.
Any ongoing R&D project if it's there from your firm?
We recently completed this, the full scale loading or rather full scale test for two structure, and that tests were conducted first event, earthquake event, second earthquake event, third earthquake event. So the same structure was subjected to three earthquake event
Okay.
without any repair. And we
Okay.
found that the structure has adequate ductility as well as there were hardly any cracks. That exercise has been completed. As far as blast loading is concerned, see, all the residential buildings are not supposed to be designed for blast loading.
Yes, sir.
It's only required for important structure like nuclear reactors or airport buildings or parliamentary buildings or hospitals, few selected hospitals, the particularly few connected links, infrastructure links, bridges and all, those are supposed to be designed for blast forces, not all the structure, because otherwise the cost of construction will be enormous and the probability of getting the blast loading is hardly anything. The life of the structure, the housing, particularly today's session is on the housing.
Yes.
So what exactly is what is the life of housing typically in India? 50 years is considered as a reasonable life of any housing. Why 50 years? The critical factor is that after every 10 years, our development control regulation changes. About 20 years ago in Pune, the FSI, permitted FSI was only 1.1. Now it is 2.5 to 4. So every occupant after 30 years wishes to increase their house. So they opt for demolition of the house
Yes, sir.
and get the additional FSI. So typically we must think of to what extent the we should spend in housing for that particular service life.
Yes, sir.
So, any other query? Okay, so thank you so much, sir. On the behalf of the organizing team and the participants, I extend heartful gratitude to you for delivering such a insightful and inspiring session today. Sir, your valuable experience and deep knowledge of the precast and prefabricated construction and technology and the vision for the sustainable urban development have truly enriched our understanding. And again, your practical insights, real world experience, and live testing videos how you shared will surely guide us in our professional and the academic pursuit. Thank you so much, sir. Thank you.
Thank
Sir, at
you.
the last, I would like to add one thing, sir. Even if people see such thousand presentation, the work you have done in the field, it's very hard to even imagine for all of them. Because I was there in BG Shirke and I know that in those days, whatever structure we were handling, those are so complicated that people could not even imagine that this many complication could be there in any one particular structure. So again, this your lecture is again very well organized, sir, and it was very nice again to see all those images and all those models which we have developed since last so many years as a precast element structures. And again, thank you so much, sir, for enlightening us.
Thank you. Thank you. Thank you for your kind words. I
Yes,
request that since you all are faculty members,
yes,
my sincere request is that visit our site, visit our factory, hmm, plan a visit. See, the factory at Mumbai is the single largest factory in Asia. So everything is available in India unless the faculty knows that these things are happening in India on such a scale. you will not be able to emphasize or create the interest in the students. And the industry needs students who are having this kind of exposure and this kind of inclination. So my sincere request is that please plan a visit to Mumbai. Maybe our site is just going on in Nagpur also at Empress Mill. We are building one commercial building at Empress Mill. So the construction has just started, but the factory is not at Empress Mill. The factory is quite far away. The best site which you can visit is Mumbai at Navi Mumbai, Taloja.
Sir,
So
we
plan a
shall.
visit. Do let me know whatever is convenient to you. We will be most delighted to showcase what exactly is happening in precast construction. Thank you.
Thank you so
Yes, sir.
much.
Definitely, sir. We will plan something so that people will understand about all these precast element structures.
Yeah, yeah, yeah.
Yes.
And also try to start a course
Yes, sir.
on precast
Definitely.
construction.
Yes, we have the courses, sir, but yes, the work which we do in the field, it is completely different from the work which we study in the, you can say, syllabuses or
Yeah,
courses.
yeah. That's so. The best way is that have some industry experts,
Collaboration, yes.
call them collaboration, call them for presenting the case studies, some design studies, some research studies, so that the students will get exposed to such innovations or such advancement.
Yes, definitely, sir. Thank you very
Thank
much
you.
once again, sir. Thank you,
Thank
sir.
you.
Thank you,
Thank
sir.
you.
Thank you so much, sir.
Thank you.